So let's discuss next problem in classical mechanics. So here is the problem. So the two ends of an inextensible string of length L and mass m are fastened together on a circular loop and set spinning about the center of the circle with uniform angular velocity omega. The tension in the string is so here what they are saying is two ends of an inextensible string of length L and mass m are fastened together on a circular loop. That means let this be circular loop, and what we have to do is two ends of an inextensible string of length L and mass m. So we have to take a string, its length is L and it is of mass m, and we have to fasten it together on the loop, that is like this. We have to just attach this string to this, that is fastening tightly. We have to just make that string to align along this circular loop. So just attaching it, we have to tie it, we have to fasten it and set spinning about the center of the circle with uniform velocity. So now what we have to do is this circular loop has to be rotated. That means it has to be spinning. So it would be rotating, keeping on rotating, spinning with the angular velocity, uniform angular velocity omega. The tension in the string is, so now we have to find out what is the tension in this string. So in this string, so it is held on, it is fastened along this circular loop and it is also spinning. So because of that we need to find what could be the tension in this string. So now what we have to do is, in order to solve this, consider a elementary length of the string dl which subtends an angle delta theta at the center. Drawing a free body diagram for this elementary length. So we need to consider a small length of the string, that is, so this is the entire circular loop. So we need to consider a small portion like this. So this small portion here, so that is the diagram here, over here. So this is the circular loop and this is the small portion of the string at that. So here we need to consider string of length dl. So this is of length, entire length of the string is L, small l, only this much if we consider. So its length is dl and it subtends an angle delta theta at the center. So here this is the center of the circle. So if you see from here to here, it is subtending some angle at the center. So that is nothing but here, it is represented over here. So this is the entire length of the string and at the center. So this is the center and the loop is of radius r, small r, and it is subtending an angle delta theta. Actually it is delta theta. Here it is, we have taken delta theta. So this is delta theta. So it is subtending an angle delta theta at the center. Subtending an angle delta theta. So this dl length of the string. So it is making an angle delta theta at the center. Now by using this we need to draw a free body diagram and find the tension finally. So here tension would at each point on the string would be acting in tangential direction. So at this point I have drawn tangent. So at this point also in tangential direction the tension will be acting. That is here it is acting in this direction and here it is acting in this direction because the string is held tight. It is made to be held tight, fastened on this loop. So it is lying on that loop and it is tied and it is fastened. So some tension would be acting. So at this point it is acting in this direction, in tangential direction, and at this point it is. So it has to maintain circular shape. That string has to maintain circular shape, and we are making it it is maintaining the circular shape because of this tension only. So because of this tension here, as if it is tied there in this direction, as if it is suspended there in this direction. So here tension is acting in this direction, tangent at that point, and here also the tension is acting at this direction, tangent at that point, and the tangent is perpendicular to radial. So tangent is normal to radial direction is normal to tangential direction. So this is tangential direction and this is radial direction. In this direction is nothing but radial and this is nothing but tangential direction. They both are perpendicular to each other. So now what we have to do is, so if this entire angle is delta theta from here to here, so half of this angle would be delta theta by 2. So this angle would be delta theta by 2. In the same way here also this angle would be delta theta by 2. Now what we have to do is draw a parallel to this line. So this is the line, midline. So this line divides this delta theta angle into two equal halves. So a line parallel to this line. So this is that line. And here this is tangent. So this is its own components. So here this is the tension and it can be split up into two components. So like this is one component, two perpendicular components. So this is one, this line would become one of the perpendicular components and this is another component, this direction. So this is a resultant tension and its components can be split up in two perpendicular directions in this manner. So these two perpendicular directions. So now, and next thing is, so here this is delta theta by 2. This line is parallel to this line. So if this angle is delta theta by 2, then this angle would be delta theta by 2. These two lines are parallel. So as this angle is delta theta by 2 and this angle would also be delta theta by 2. And this angle would be 90 minus delta theta by 2 because this is radial direction, this is tangential direction. Both of them are perpendicular to each other. If this is delta theta by 2, then this has to be 90 minus delta by 2, 90 minus delta theta by 2 because sum of these both angles should be equal to 90 degrees. Hence this angle, if this angle is delta theta by 2, this is 90 minus delta theta by 2. Again this is a right angle. So the two components are perpendicular to each other. If this is 90 minus delta theta by 2, then this should be delta theta by 2. So this overall angle is 90 degrees. So if this is delta theta by 2, 90 minus this is delta theta by 2, this is 90 minus delta theta by 2, then again this also should be delta theta by 2 because this is again a right angle 90 degrees whose sum of all the angles is 90 degrees. Over here this angle, sum of these two angles, so this is delta theta by 2. Now this is nothing but t cos delta theta by 2, this component, and this component is nothing but t sin delta theta by 2. So two perpendicular components. So t cos delta theta by 2 and this is t sin delta theta by 2. And here also this is t in the same manner. Here also if we resolve like this, this is delta theta by 2, here also we would get delta theta by 2. So from there this is t cos delta theta by 2 and this is t sin delta theta by 2. So if you see here finally, if we see here, so this is acting in this direction, t cos theta by 2, t cos delta theta by 2, and here this is acting in this direction, exactly opposite direction to this t cos delta theta by 2. Hence this both would get cancelled for this particular length of the string, dl length of the string. These two forces would get cancelled, this t cos delta theta by 2 and this t cos delta theta by 2, because they are acting in opposite directions. So only force would be remaining on this dl length of the string is this, that is t sin delta theta by 2 and this is t sin delta theta by 2 would be remaining. So this is t sine delta theta by 2 and this is t sine delta theta by 2. These two are acting in the downward direction, but these two are acting in exactly opposite direction, so they would get cancelled. So now only these two would be remaining, this one and this t sine delta theta by 2. So overall the net force acting is equal to this one plus this one added together, we will get 2t sine delta theta by 2, 2t sine delta theta by 2. So these two forces would get added, that is anyway 2t sine delta theta by 2. And again, as this loop is spinning, because of this it is in circular motion, we would have radial force, that is nothing but mv square by r, or else mr omega square. So this force is equal to this force. Because of its spinning motion, we would be having radial force. So the force because of this tension is balanced by this radial force acting outward. So mv square by r, that is nothing but mr omega square. And here, as we are taking only this dl length of the string, hence here mass is also delta m. As we are considering only dl length of the string, its mass is delta m or omega square, mv square by r or mr omega square. So now here if you see sine delta theta by 2, here this angle is really small, delta theta is very small, and again delta theta by 2 is still small. That angle is delta theta is small and delta theta by 2 is still more small, and we know that for small angles sine theta, so that is for small angles sine theta is nearly equal to theta. So just like sine 0 is 0, sine 0.001, like that you get nearly equal to that angle. This is only for small angles, not for all the angles, that one we need to remember. So here sine delta theta by 2 is nothing but delta theta by 2. This only delta theta by 2 would be, so sine theta is nothing but nearly equal to theta. So in the place of theta we are having delta theta by 2. So here we are in delta theta by 2. Next is mass of this string, dl length of the string. You know that mass of l length of the string is m. That is the string, total string is of length l. So its entire mass is m. So mass per unit length of the string is nothing but m by l. So this is actually small l. So mass per unit length of the string is m by l. And mass for this much length, so here length is dl, and we know that l is equals to theta is equals to l by r. So theta is equals to l by r. Here theta is nothing but delta theta, and l is nothing but dl, and r is nothing but this small r. So delta theta is also dl by r. So then dl is also r delta theta. So length of this string can be expressed as r delta theta. So m by l is nothing but capital M is mass of this entire string. Capital M is mass of this entire string, and m by l is mass per unit length of the string. And this string is having some length. So in order to get the mass of this much length, that is nothing but you need to multiply it with that length, that is m by l dl. So dl is nothing but r delta theta. Hence we are having in the place of delta m this term. And here if you see delta theta would get cancelled, 2 would get cancelled, only t would be remaining this side. And here m r square omega square by l, that is m r square omega square by l. But we know that l is also 2 pi r, that is the circumference of this circular loop is nothing but 2 pi r, and along that circumference we are fastening this string. So that is the thing we are doing here. So this loop is of radius r, small r, and its circumference would be 2 pi r, and along that circumference we are fastening this string of length l. Hence 2 pi r is equals to l, string's length. Hence we would be having r is equals to l by 2 pi. R is equals to l by 2 pi. So that one we need to substitute in this l's. Then what we would get in the place of r, l square by 2 pi whole square. So l square by 4 pi square. So l would get cancelled. Then we would have m omega square l by 4 pi square. In the place of 2 pi, 2 pi whole square, that is 4 pi square. After substituting here, one of the L's would get cancelled. We would get finally tension of the string has this. So T is also m omega square L by 4 pi square. So m omega square L by 4 pi square. So D is the correct answer for this problem. So this is the required problem and its solution. So thank you.